Welcome, everybody. This is the first edition of what we call live from behind the walls, the university walls. Last year, we started a series of webinars for the Into CPS Association. Now we are trying to expand that, and we'll try to have these research webinars more frequently and try to couple different things together. This is now organized in something called Orbit Lab, who are more professional at doing these things than what we have been doing in the past. In a sense, it's going to be a format that we are trying to find out what's going to be best. It's going to be 2 hours, very short presentations. And before we begin, I'd like to tell you that the session here is going to be recorded. So if that's a problem for you, you should leave. I'd also like you to all mute and remove your cameras when you're not speaking. And then, in a sense, I would like to welcome you all. And those of you who don't know me, my name is Peter Gorm Larsen. I'm professor at Aarhus University at the Department of Electrical and Computer Engineering. And here you see the program for today. We will start off with a presentation by my colleague Hugo Macedo about the HUBCAP project. It's an EU project that we are coordinating from Aarhus. And then we would have one of our research collaborators from NTNU in Norway. This is Lars Ivar, who are going to be talking about digital twins for ships. This is followed by 3 presentations that are from my own group, related to digital twins and co-simulations. Casper Thule will first present a new version of our Maestro co-simulation orchestration engine. And then instead of Christian's talk, because he's having a course at the moment, we'll move that down. We will have a former guest PhD student of ours, Maurizio, who will be talking about the modeling and simulation of attacks on cyber-physical systems. And he's coming from Italy. So he will be jumping in up here, where otherwise we would have seen a presentation, which we'll see later on then, by 2 of my PhD students about trying to introduce something called UniFMU. And then this is followed by another PhD student that is talking about synthesizing co-simulation algorithms. So after those things, we will have a guest talk by one of the members of the Into CPS Association from Raytheon Technologies Research Center in Italy. Actually, they're now called Collins Technology Research Center, I believe, but these things change so frequently. That's the presentation we're going to have from Pisa. And then finally, Casper Jensen, who is the responsible person for Orbit Lab, will give you an overview of what Orbit Lab really is, because this is a collaboration both for students and also for research activities. You're going to see a number of presentations. They were quite short, and we have not made time for questions during the program, but you're welcome to ask questions in the chat. The point is that when you begin your question, you can kind of state the name of the speaker or the talk title, and then it should be clear who should be answering the corresponding question. Obviously, we will subsequently, for those of you who are registered for the events, also give you access to the video and also to the slides in case the different presenters are sharing the slides with us. So I'm going to shift into this kind of series of having next year. The target is to have one of these webinars every month. And it's because the number of projects is growing. This is just a project that's in my research group. The one that's at the top was funded and started up 2019. All the other ones have been funded and started 2020. And you will see some of the other people who are here are just friends of us. And I'm now also heading a section. So we are having more people who are doing research than just in my own group. We also have a number of PhD students, number of postdocs. You're going to see some of them here today. Christian, Daniela, you're going to see Casper, and Hugo will be talking as well. And some of the others you're going to see at a later stage. So at the end of the meeting, where I kind of close it, I will come back to remind you what the next events are and give you details for how you can register to talk and present at those events in case you have an interest. So with those words, I would like to stop sharing my presentation and ask Hugo to share his presentation.
Yeah, so I'm in progress. Let me just, yeah.
And welcome to all of you who have come in the meanwhile.
Yeah, hello everybody. Like Peter said, my name is Hugo. I'll be glad to answer your questions about HUBCAP. So starting from now, like kind of here we are, and let's talk about this EU project that we are coordinating at AU. So yeah, we are funded by this Innovation Action by the European Commission. It's a project that is to last until December 2022. And basically, we want to provide this one-stop shop for European SMEs that want to use or like kind of adopt model-based design or provide model-based design tools to an ecosystem of SMEs that are interested in or developing cyber physical systems. Yeah, so most of us in this in the panel probably know what it is, a cyber physical system, but because this is a video and like kind of some of us may like kind of not be so aware, I'll try to just lay out like kind of in layman's terms what would be a cyber physical system for us. So like kind of here are examples. So actuators or an aircraft where like kind of there's like kind of surfaces that need to be controlled. And electrical scooter motors. Well, whenever you have computational or computation interacting with a physical process, you are working within the setup of cyber physical systems. It is known that like kind of if you're a usual producer of such kind of system, that is easy to just like kind of extract some data or start like kind of connecting it to the internet. But if you want to include smartness in your products, you will probably need to use some kind of model and model-based technologies. What is model-based design? Again, in layman's terms. So, well, basically there exists two worlds in our vision. So a system, real world part. So in this case, like kind of exemplifying it with the wastewater treatment plant. So, well, all the wastewater that our homes produce and like kind of our towns or businesses is usually channeled to a treatment plant where the water should like kind of traverse a number of tanks. And when it's flowing from a tank to another tank, it eventually has some kind of valve that controls this flow. And then if you have a model counterpart of this real world system, eventually you have either like kind of synthetic models, like an overture model, or 3D animations, or bond graphs, formalisms that like kind of describe whatever is the continuous dynamic of the flow. All of these are considered models. We are like kind of tool agnostic, and we like kind of if you bring your MATLAB model or if you bring some other kind of formal model to our environment, if it has some value, we are willing to host it. Because basically what the project wants to do is that indeed enable this interaction between tool providers, be some kind of marketplace where we have these catalogs where you can like kind of experiment with tools, and eventually we facilitate SMEs to both like kind of learn or adopt this and to test them before they invest in some products. So here are a bit of the depictions of the platform prototype that we have already. So we both have like kind of this potential that a consumer or an SME that wants to experiment with some tools they will just like kind of fill in some kind of shopping cart as in a typical web page. Then they launch the sandbox concept that our project developed, and they can interact with a tool via their web browser at basically no cost, at least in this process of testing before investing. And there's a lot of emphasis in terms of enabling collaboration between people. So in the bottom left corner, we have this highlight of like kind of one of the features of the of our platform or of our web portal. That is like kind of you are able to invite guests to control or to gain access to your to a sandbox that you may be having access inside our platform. So in this image, I try to like kind of depict how we collaborate nowadays, especially in COVID times. So we are working each one in our bubble from our homes, and there's like kind of this connection on the bottom that is basically like kind of like we're doing now. So we have some kind of chat or voice or like kind of Teams-like based system that allows us to communicate, send messages from one to the other and see each other's screens. But we all have, or normally what you would do in a model-based design approach is that you have your model replicated in different places. And eventually, if you're using a control version system, which is quite standard now, you access some kind of central repo or you have a distributed manager for the different repos. So you align your model every time you do this, every time you kind of do your own changes. But basically, the idea is that you have a local copy in your machine, you do some changes by yourself, eventually communicating with some other people through some kind of system that allows you to do video conferencing. But in the end, like kind of then you sign these changes or you commit these changes and you upload it to some kind of central repository or you just like kind of propagate the changes to everybody in your institution or with the world. And basically in HUBCAP, we expect that we would change how we collaborate. So in HUBCAP, we expect that people interact. So SMEs or elements from different SMEs can be together manipulating a joint sandbox. So that's why like kind of the figure at the right-hand side now like kind of just has this idea that, okay, the model is hosted on top of a VM that is jointly shared or jointly owned by the two entities, somehow like kind of extending how you collaborate in a different way, because instead of each one having their own systems and like kind of there's no common system among their tools, now the kind of the HUBCAP platform would allow you to just have that shared resource. So yeah, what it is this sandbox, what it is this collaboration enhancement that we are proposing to you or to the community. Well, basically is like kind of the prototype of this is just a regular website as you would have, but basically we host virtual machines like a cloud provider would host. And basically on top of these virtual machines, you can install your tools. So if you're providing a model-based design tools and you are an SME, you are already you can already apply to our calls and like kind of you can already try to deploy your tool in this scenario. And eventually you can have some models on top of those. And you can have several virtual machines if you have like kind of different components that like kind of have different requirements. But basically the idea is that these components can like kind of communicate using a VLAN and are orchestrated in a like kind of push button way to your users, so they don't have to deal with the hassle of installing dependencies or somehow like kind of having a problem like kind of when they try to use your tool. So here's the demo of one of the initial experiments that one of the SMEs of our consortium that provides model-based design tools, in fact, 20sim, Control Labs, 20sim is the tool, Control Labs is the provider, did last year. So basically, this is the sandbox. So you can, if you make it full screen, you don't see all the controls that add the additional collaboration features or like kind of allow you to really experience that you're inside a virtual machine. But yeah, basically that's it. You have a ready-to-use environment where you can collaborate with other people. So here, like kind of, they're just providing a demo of one of their models, and yeah, and we have more videos about the other SMEs in our YouTube channel. So please subscribe or look or search for HUBCAP EU, and you will find.
You don't see the video if you're trying to play that.
Oh, I didn't see that. Somehow, like kind of on my computer, I see the video.
Okay, we don't see the video.
Okay, thank you for informing. Well, I think I will just drop the link in the chat now because I lost the time for the video. So yeah. What are the research opportunities, at least from an academic point of view or research point of view? We are already facing or like kind of trying to address some of those, and obviously like kind of we are open and we foresee that if this is to become a reality, there's a lot of things that like kind of we used to do in some way that have a reason to do so, or there's a reason why we did it. Both like kind of to ensure that like kind of all these systems are secure and you don't share like kind of more than like kind of what's expected from your machine. So that's why, for instance, this by uploading this PowerPoint into this session, you only have access to the PowerPoint. You don't have any other access from my machine. But if we want to break this boundary and we want to like kind of have a virtual machine that is both like kind of owned by me and somebody else, you will find a lot of potential avenues for research, right? So who owns like kind of the jointly developed assets, right? So out of my mind, we can immediately see, okay, will we have Git commits that have several authors because both of them were like kind of doing the edits on the code, like kind of in a joint session. What kind of license, like kind of, will we need if we're really running like kind of this kind of system where you can just test these tools without any big attachment, but we don't get the tools forever, right? So maybe run it like kind of for a couple of hours for a test. What kind of license will we need to like kind of make it efficient and less costly? And well, indeed, like kind of what are kind of the security challenges? How do you ensure that like kind of malicious behavior is not like kind of extrapolating from a current sandbox? So yeah, that's like kind of the opportunities for researchers. Opportunities for EU SMEs are that we have this program with open calls, so you can apply to our open calls and either like kind of receive up to €1,000 to deploy an asset in our platform. You can join a partner, and if you're providing a tool and this partner is interested to adopt this tool, you can define a project where you both have an experiment and funding to do it. And you can also like kind of find an extra partner and do something more like kind of a big innovative action in terms of cyber physical systems. And that's it from my side. Hopefully, if you have questions, I'll be able to answer it in the chat. And well, thank you for listening.
Thanks, Hugo. Lars, Ivar, can you take over the screen, please, to give the next presentation?
Yes.
Digital twins in ship.
Let me see here.
Welcome to the rest of you who have arrived.
Okay, can you see the presentation now?
We see the presentation, yes. Go ahead.
Yes.
Thanks.
Yes, thank you. So I'm Lars Hatledal from NTNU. I'm a PhD candidate working on co-simulation. So I will talk about co-simulation as a fundamental technology for twin ship. This is also something I have published a journal on. So this is what I'm going to talk about. The background for this work is basically two projects. It's the KPN twin ship project, where we aim to develop a digital twin of the research vessel Gunnerus. And then there's the SFI Offshore Mechatronics, which is the funding source for my PhD, where I have mostly been developing enabling technologies for co-simulation that we are using for this work. So the research vessel Gunnerus, it's a small research vessel that is owned by NTNU. So we are able to use this vessel. We can install equipment on board and make them do sea trials and such, so that we can collect data. The vessel is equipped with 2 azimuth thrusters, a tunnel thruster, and it also has onboard equipment such as a palfinger and a frame crane. It also has a ROV. We have a simulation model of this ship that is modeled in VSIM by Sintef Ocean in Trondheim. In 2009, the vessel itself was elongated, so they increased the length of the ship. We have a model that has of this non-elongated ship that has been verified against the sea trial data. And we also have a new version of the model that represents the elongated version. However, this model has not yet been thoroughly validated, but it's based on the old model. So we want to use co-simulation to make a digital twin out of this ship. And why do we want co-simulation? Well, co-simulation allows us to do model sharing. We can run models independent of the implementation tool. It allows us to protect the protection of intellectual property, where the FMUs or the models can be seen as black boxes, where the user does not necessarily see what's inside. And when we are doing modeling of a vessel, it requires many different domains, and using co-simulation, we can do domain-specific models, can be written in domain-specific tools. So you can have one part of the system being hydrodynamic and another electric, and you can do those in different tools. The tool that is best used for that domain. And then we can create complete systems as an aggregation of then independent subsystems. And co-simulation is scalable. At some point, a system may grow too large for a single computer. And co-simulation allows us to distribute and also perhaps parallelize the workload of simulation. So this is the basis for enabling digital twins, where we replace the mathematical models with a real asset without having to change the system structure of the simulation. So I have developed some enabling tools for co-simulation that is used there. The first one is FMI4J, which is a tool for importing and exporting FMUs for the Java virtual machine. And then we have Python FMU, which is a tool for exporting FMI 2.0 for co-simulation FMUs from Python code. And FMU proxy, which allows us to wrap existing FMUs in a new client-server-based FMU. And this allows us to create multiple instances of models that do not have that opportunity. And it allows us to run FMUs on different architecture. For instance, if you have a model that only runs on Linux, but you want to simulate it in Windows, you can run the FMU in Linux and use FMU proxy to access it from Windows. And then there's another tool called SSPGen, which is a Kotlin domain-specific language for easing the creation of SSPI-compliant archives. And SSP, that's a standard for defining the system structure of simulation. So where FMI is for independent models, SSP is for the complete system. So SSPGen makes it easier to create such systems. So these are tools that we use to enable co-simulation of the Gunnerus. So the steps we take towards creating the twin ship is that first we retrieve existing models or FMUs from the OSP reference models. So the OSP stands for Open Simulation Platform. They published a set of maritime reference models that are public, consists of, for instance, thrusters and the hull and so on. So we can take ready-made models from this repository. And then we can develop supplementary FMUs, for instance, in FMIFIOD, Python FMU, or some domain-specific tool. And then finally, or then next, we can define this system using the SSP standard, using SSPGen. So which models do we want, the connections between them, the initial values of the variables, and so on. This is defined using SSP. And then we can then simulate this SSP in any SSP compliant tool. Currently, the open source compliant tools today are Vico, LibcoSim, and OM Simulator. And hopefully there will be more in the future. So the system configuration of the Gunnerus co-simulation looks like this, that I used in the journal paper. It consists of 8 FMUs, where there are 10 instances of the models with 48 variable connections. So we have the hull, we have 2 azimuths, we have a power system for the azimuths, and then we also have some controllers to control the speed and velocity of the ship. The idea behind co-simulation, this particular co-simulation, is to check the power consumption of the real ship against the simulated ship. So we see that from the list of FMUs here, we see that some of them cannot be instantiated more than once per process. So in order to run this on a single computer, we need to run distributed, or to have 2 instances of, for instance, the thruster drive or the azimuth, we need to use FMU proxy in order to be able to have 2 instances in the same simulation, because they need to run in separate processes. So FMU proxy is ideal to just wrap the original FMU into a new FMU that supports this. So this is just an overview of all the variables that are connected to each other. So it's a bit complicated system. And the preliminary simulation results from this case, we can see some of those results here. So the thing is here that we are taking pre-recorded data from the ship from a previous run. So we store them as CSV and we use those in this case. We don't have a direct link to the Gunnerus yet. So we take pre-recorded data and plot those, and then we create this at least a preliminary digital twin, and we use controllers to control the heading speed of the vessel, and then we compare the power consumption. That results can be seen here. So as we can see, there are some discrepancies between the measured power consumption in blue and the simulated power consumption in red. So there are 2 reasons for this, perhaps. The model probably needs to be tuned more, the hull or the azimuths. But after 1200 seconds, we see something that can be perhaps explained by environmental forces, because the blue line is the power consumption of the real ship. It decreases, while in the previous slide we see that the surge speed actually increases. So that could mean that there are environmental forces acting on the hull, and perhaps in the future we can use the data to estimate the environmental forces applied to the real hull based on the simulation data. So as I said, we don't have a live integration with the Gunneris yet, so we used pre-recorded data. So we need to collect and transmit the onboard sensor data in real time. So we need to collect data from the different vendors and systems on board and publish that data over 4G using, for instance, MQTT. And then when we have all the data we need, we can package an MQTT client as an FMU and drop it into the simulation, replacing the previously recorded data. And then we would have a live link to the vessel. The data itself would be updated approximately once per second. So there is some challenging to this. We already have a computer on board sending some of the data, but NTNU owns the ship, but not the data. So we need to negotiate with the different vendors so that we are able to actually get the data that they own. But once we do that, we would have access to all the data that we can use that in real-time simulations. Conclusion here is that co-simulation allows cyber-physical systems, such as the vessel, to be simulated using models from different vendors and tools, which is great, because then, of course, you can have different domains in one simulation. FMU proxy enables Gunneris system to be run in a non-distributed co-simulation masters. SSP allows the system to be defined in a standardized way, so the simulation itself becomes tool independent. Further work on use cases is required, such as closing the loop by providing actionable feedback to the crew. And how can the crew benefit from the insights provided by the simulation? And that is what I had for you today.
Thanks very much, Lars, Ivar. That was very, very valuable. And you can see this is a new collaboration that we are establishing with NTNU because they are using co-simulation very similar to what we are doing. And what you'll see next will be Casper Thule talking about the new version of our Maestro co-simulation orchestration engine. So Casper, if you take over the screen, we have it there. And this is some of the work that's supported by the Paul Due Jensen Foundation, which is common from the different presentations from my research group. So Casper, over to you.
Thank you. So Lars, Ivar has already given a nice introduction to co-simulation, so I'd rather not spend too much time on this, but roughly it's about that you have these simulation units represented up here, and they are black boxes. Each of them has a static description file describing inputs, outputs, parameters, and some functionality. For example, whether you can get and set the state. The communication is via set input, get output. Time progression is via a function called doStep, where we tell it how much to progress in time. And an FMU can reject a time step, maybe because it destabilizes the model, in which case it will report how far it was able to go. Now, in some cases, you can perform a rollback, which is difficult with digital twins because you can really roll back the real world. But in a model environment, this is some case possible. So the current Maestro has been quite successful in the process projects it has participated in, but it was rather monolithic and challenging to extend. Furthermore, for many of the projects we joined in where people were learning how to do co-simulation and FMI, it was difficult to get to understand how it actually executed. So the new Maestro will be for research, teaching, and industry-related projects, and for digital twins. So the idea is that it should have all of these nice features, basically everything. So the way we approach this is that we build a framework, and we also build a domain-specific language. So this has been used, for example, for fault injection, where Migita has created a fault injection plugin. And the idea is that we provide a baseline and other people can help extend the framework. So when you write the Mabel, we have some different options. The raw Mabel, which is a domain-specific language, is rather C-like, as you can see from this here. Here is a function where you set a real parameter on an FMU, but it's quite close to C. So typically, we would assume this was a generation target. But once you have your simulation specification, you can do manual prototyping here. And this has been rather useful when debugging FMUs. Furthermore, it's useful for reviewing if the co-simulation actually carries out as you want it to be carried out, which is interesting in context of prototyping, where you're not exactly sure what your master algorithm should be doing. We also expect to use this model for teaching and learning how the FMI standard works, and also the new FMI 3.0 standard. So one of the bad things about this is that you're really lacking an ecosystem to write this. It's very verbose. Now on the good parts, it's quite simple, it's expressive, but it's also tightly coupled to the DSL, which is both a good and a bad thing. Now you can also go on the next level where you can write directly on the AST. This is sort of internal. We have been doing before. We actually managed to build the API. So with this, you have the whole JVM ecosystem to help you. You can write expansion plugins. Here's an expansion plugin, which you in turn then can use over here in Mabel. So it can assist you in writing your Mabel specification. Such an expansion plugin will then be expanded, meaning that this down here will be removed and replaced with the actual code that it generates. So if you work directly on the AST, you have the whole JVM ecosystem. It's quite expressive still, but you're very tightly coupled to the implementation. So you can also go the higher level approach, which Simon will tell you about later. Now they have something called a scenario verifier, and this is very abstract. Here's an example of a co-simulation step. You save the state of two FMUs, and then you loop until certain variables converge. Here is how you set inputs and how you do a step. So in this case, this is used for verification and not so much execution, but we're working towards using Maestro 2 as an execution engine for such a notation. So if you look in terms of abstraction, then we have C, which is too low level for many of the people who are interested in co-simulation. We have the Mabel DSL, which is still too low level, but a bit more abstract. Then we have the AST. Here you're basically working in Java, but you're still working quite a low level. And then we plan for the API to situate here, which means that it's above the AST, but still below the scenario verifier, as you see over here to the left. And the reason for that is that we want it to be executable. So the way we're going about this is that we center it around a scope approach. A scope is like you know it from various programming languages. It's sort of a top level entity. In a scope, you can create an FMU, and here we expect it to maybe support. Now we have FMU, but we could also support other ideas if we find out that FMI is not expressive enough for digital twins. You can store variables. You can also enter different scopes, and you can activate a scope, which means you can jump between scopes when you're code generating. We also have something called a dynamic scope, which follows the current active scope automatically. So the way you can use this is, for example, down here. You create a builder, and you get the dynamic scope. Then you can store variables. In this case, you store time, and you store the step size. Now you can enter a scope, enter while, where you add the step to time, and you check that it's less than 10, which would be the end time of the co-simulation. Now this new scope is automatically activated as well, so you can keep going. And this is still rather raw, but the baseline is there, which means that we can add a DSL on top of this to make it a bit easier. So for a brief example, we have the classical water tank. I think the 20sim people will recognize this. We have the minimum level and the maximum level, and the water is supposed to stay between here. So there is a continuous model of the tank modeling the inflow and the drainage, and it reports the current level. And then you have a controller, which is capable of opening or closing the valve. So the controller has an output called valve, and the tank has an input called valve control, and the tank has an output called level, and the controller has an input called level. So the way to represent this in using the Mabel API is by using ports. Ports are a representation of an input or an output or a parameter, basically a variable of the FMU. Now you can link these together. So the way this is carried out is that you instantiate the FMUs, or first you load the FMUs, then you instantiate instances of the FMUs, and then basically down here you can link the variables. So as you can see here, we abstracted the value references, which are basically numbers, and we allow names instead for the generation purposes. Once you've done this, then you can retrieve values to local scope. For example, this is something that you need for convergence testing. You can share them to a global scope, and then you can, if they're shared, you can set them effortlessly. So here is you get the valve, you share it to the global scope, and that means you can just call tank set linked. This makes it quite easy to create different co-simulations. Claudio is currently working on a paper where he has a state machine where we have two different co-simulation algorithms running, and this has been executed using Maestro 2. So for a brief demo, I had enough failing live demos to not do this live. So basically what you can do is that you can have a co-simulation and express it, and then you can execute it, and it will give using the API, and it basically will give you something like this. So this is with error handling, where you can see that we basically have we import different runtime modules, and we have a lot of logging. So this is typically code generated. We hope to make some effort on making this understandable code generation, which I'll also show you briefly. But basically, this is expressing a co-simulation algorithm, rather low level. So if we try to go back, then you can also disable the error handling, and you will get a much nicer co-simulation where it's easier to see the calls that are actually occurring. And you can use this for teaching purposes to explain how the FMI standard would work for a given study. So the reason why it's low level is also that we keep in mind that we want to code generate this, for example, to C++. And the reason that we want to do this is that we expect for the digital twin that performance will be in the center of the digital twins. So in order to keep up with performance, we expect that we need to be able to code generate and run on a machine level. You can also go to this link, which you can see in the slides afterwards. I'm going to share them, where you can actually see the test implemented in Java and run it yourself if you're interested. So in terms of research ideas, we have lots of them. Some of them are nested and hierarchical co-simulation. How can we create a sound hierarchical co-simulation where the sort of nested level is a co-simulation itself? We're also looking into automated verification. Simon and Claudio has done some nice work on a scenario verifier that Simon will show later. But we're also interested in enriching a Mabel specification, which, for example, notations like this, that might make it possible to extract these notations and then perform automated verification. We might implement a language server protocol so we can code this in VS Code. And some of the things that we have on the drawing board is parallelism in this language. How can we support design-based exploration, both in context on running it in Java with an interpreter, also going all the way to C++. We have currently enabled environment variables at both levels, such that you can code generate a specification once and then just change the environment variables without having to recompile the thing. We will look into SSP, probably using Lars Ivar's work. And then we're also going to look into X in the loop. And obviously we'll try to use this as an orchestration engine for digital twins. And that was it. Thank you.
Thanks, Casper. You didn't talk about the performance gained with the new one compared to the old one, but that doesn't matter too much. We'll hear more about that later, I'm pretty sure. It's
the performance is not new. That's why I was not part of this presentation. It's still very performant.
That's fine. Good. So now we should have had a talk by Christian Ligar and Daniel Thule. What I suggest is we jump and we kind of have the presentation by Cinzia and Maurizio. And so if Maurizio, if you could share your screen now. Thank you.
Yes. Okay, so I can start.
Yes. Go ahead. And remember, you can write your questions in the chat. Please write the name of the presenter first or something like this, and then go ahead, Maurizio.
Okay, so thank you for the introduction. So this talk will be about modeling and simulation of attacks on cyber-physical systems. So basically, we all know that cyber-physical systems are often critical infrastructures. For example, the ship that was mentioned earlier, I think it's pretty critical. And also in that use case, the security is a main issue. So basically, we want to provide a model-based design approach to analyze the resilience to attacks in cyber-physical systems. So we will analyze data alteration in the interaction between plant and controller. We are going to use the prototype verification system for formal analysis. We will analyze the attack injection rules. We will use co-simulation to evaluate the effects of the attack. and then the PVS theorem prover to formally prove the resilience to attacks. So this is the general architecture of a cyber-physical system. We have the plant with the sensor and actuators, and we are considering the controller as an endless loop in which reads the input, computes the output, and actually writes the output. The attack are modeled with the functions. So we might have a sensor attack that corrupts the input data, or an actuator attack that corrupts the output data. Of course, this approach requires some knowledge of PVS, because we write the controller in PVS and we extend the controller with PVS. The advantages is that the structure of the co-simulation is not changed, so we are not adding any extra FMEU to the scenario. The same PVS model can be used for both co-simulation and formal verification, thus providing verification and validation of the model. And we will also allow interactive attacks thanks to the PVS-IO web extension of PVS. So a few considerations on the attack. We are going to consider attack to sensors. This attack can alter the value of local or hidden variables of the control. They can affect logging and tracing mechanism, but they can also be masked and confused with fault happens. We are also considering attack to actuators, which usually have more impact on the behavior of the system, and also a combination of both of them. Of course, all the attacks can be triggered under different conditions, mostly depend on time conditions. So, for example, always after a specific time step, during random or periodic intervals, only once, or any possible combination. So, formal modeling the attacks, we are going to model an attack A with 3 sets. The first is var A is the set of control variables altered by the attack A. Then we have a set composed of clock A, which is the local clocks of the attack, and step counter that represents the global time. And then we have the command A, which is the set of guarded statements. So when a certain condition is met, some variables are actually changed. So this is a skeleton of a PVS attack function. So the attack function takes as input one extended state. The extended state is the original state of the controller plus the clocks of the attack and the step counter. The return of the function is another extended state where if the certain condition is met, then some variables are actually changed. If the condition is not met, the state is has no changes. We have used the line follower robot as a case study. This is a very well-known robot provided by the Into CPS Association. It has 2 sensors and follows a line painted on the ground. We have implemented a stacked attack to sensors, which basically forces the left sensor to a certain value after a random time step. Basically, it uses only one clock, clock 1, and when the step counter becomes greater than clock 1, the left value of the sensor is forced to 140. We have some knowledge. We require some knowledge of the controller. The controller uses 150 as a threshold, so values below this threshold means black. With PVS, we have written a theorem, so we can prove that under this attack, the power of the left motor is always lower than or equal to the power of the right motor. So we have used a random function and random, and for every step k above this quantity, the absolute value of the left motor will always be less or equal to the absolute value of the right motor, which means that the robot will never be able to turn right. Another attack that we have modeled is an attack to the actuators, and this one basically randomly switches off each motor for a single step. It uses two clocks, clock 2 and clock 3. It affects the motor speed, so both the motor left and right. And basically, when the two clocks are equal, both the actuator's output takes 0 as value, and the clock are resetted, the one to a random value and the other one to 0, and then later this function will be called again when this condition is met. So let's see some results of the co-simulations. We have the vanilla case, the one without any attack. So as far as concerns the actuator attack, we can see that the behavior of the robot is more or less the same with respect to the vanilla case. But we can see that at the end of the same simulation of the same duration, the path of the robot is slightly different. He has not yet completed the lap, while in the vanilla case, he has almost completed the lap. As far as concerns the sense of attack, the co-simulations have validated our formal analysis in the sense that when the attack kicks in, the robot starts turning left. He makes some sort of a circle, and he never will never be able to follow the path again. We can also model interactive attacks with the PVS IO web extension of PVS. So we can create a user interface. This user interface, we can choose when to actually start the attack. So when the user pushes, for example, actuator 0, it implements the attack actuator 0 that switches off both motors. When the user pushes the sensor left black, it triggers this other function that forces to black the values of the left sensor. And with the stop button, the user can stop the attack and let the robot follow his traditional control algorithm. So in this example, we can see that at a certain point, the sensor left black attack was activated, and the robot started to turn left and make the circle. And then, while it was in the middle of the path, in the center of the path, the actuator 0 attack was selected, and then the robot just got stuck in the middle, in the center of the path. There are some limitations to this interactive attack. So the attack is now not dependent on the co-simulation step. It depends on the choices of the users. And the problem is with these values assigned to sensor and actuators, because they can be different values, but they cannot be changed during the co-simulation. So we can move one step forward. We can also model the plant with PVS. So this requires another extension of the state in which we also include the variable for the plant from the plant. So for example, the X coordinate, Y coordinate, the angle for the direction, linear speed, angular speed, and actually the step size of the co-simulation. Then we update the time progression function with also function that evaluate these, that compute these new variables. In this case, it's just update position and update speed. So I will not enter into the detail. These functions have been created using data coming from different co-simulation runs and from the analysis of the model. We can use co-simulations to compare the behavior of the new system modeled entirely in PVS with the original co-simulation provided by into CPS, which is in which the plant is modeled with the 20 sim, and we can set some sort of tolerance, and if the PVS system does not achieve a certain tolerance, we can improve the system with a more detailed functions for the plant. In this case, we decided that an error of 5 centimeters was tolerable, so we use this model. And with this model, we can verify many properties. One of them is we can state that if a certain hypothesis on the number of steps of the attack and the step size is met, then we can say that within the L steps of simulation, the y coordinate or the x coordinate change at most of 0.015 meters, which is the reasonable value for the width of the black line. So as a consequence, we can say that any attack that satisfies this hypothesis will never drive the robot away from the line, because at least one of the sensors will still be on the line and will still be able to follow the line. Of course, conversely, if we have defense mechanism, we can say that if this mechanism allows us to satisfy this hypothesis, the robot is safe. So this is the PVS expression of this property. And basically now I can just summarize the whole work. So basically we have allowed the study of attacks in cyber-physical systems using formal methods and co-simulation. So we have provided an easy way to include the attacks in PVS model. So I hope this will encourage the use of formal methods in model-based design. And these extended models, PVS models, can be simulated together with models from different tools, 20sim or Simulink, and many more. So enhancing the validation of the PVS model, reducing the effort required to formally specify a cyber-physical system, and exploiting the advantages offered by well-known tool chains, such as the Into CPS toolchain that allows also design space exploration, for example. So this work has been published on Journal of Computer Virology and Hacking Techniques, and it is available on GitHub. So thank you for your attention. This ends the presentation.
Thank you, Maurizio. Thanks for an interesting talk here, also related to some of the degradation work that we are doing in other projects here at AU. Simon, could you share your screen, please, and give the next presentation? Yes, there we are. Thank you. Over to you. We can't hear you yet, though.
And now I guess you can.
Now we can, yes.
Perfect.
Thanks.
Yes. When I will go on, I'll talk about like synthesizing co-simulation algorithms with step negotiation. So first I'll talk a little bit about co-simulation, and then the rest of the course will be like the rest of the presentation will be around synthesizing master algorithms. So you have already heard quite a lot on co-simulation. So I'll just say, okay, it's a simulation technique to explore the behavior of a cyber-physical system. So when you're running a code simulation, you have these different simulation units, like we often call them FMUs, which you couple together by saying like inputs and outputs, they share the same value. And then the simulation is really about exchanging values between the different simulation units and then calculating their new states or their behavioral trace. And then it's an orchestrator, which we also refer to as a master, that drives the simulation. And then the combined behavioral trace of all the simulation units, that's the co-simulation. And of course, like the goal is that the co-simulation should represent like a real world system. So when we look at the orchestrator, it's really an algorithm that describes like how like each of the simulation units acts during the simulation, how are data being exchanged between the like simulation units, and how are new states calculated. And yeah, we have shown like the high level, as Casper he told you about earlier, where you like get an output using the get function, you calculate a new state using the do step function, and obviously the result of the co-simulation is extremely dependent on what you do inside the master algorithm. Yeah, so we can just look at like what can make a co-simulation incorrect. And of course, if you have an error in one of your simulation units, then that obviously affects the co-simulation result, but also an incorrect or non-optimal co-simulation algorithm would also have a big impact on your co-simulation result. And it could simply be that values are not exchanged in an optimal manner. It could also be that like if you have any kind of algebraic loops in your scenario, but they're not being stabilized. It could simply also be that the simulation units are not synchronized. And I'll get back to this in this presentation. And my primary focus is on detecting such incorrect algorithms and creating correct ones. So co-simulation algorithms, why should we bother about this? So basically, like co-simulation, it has a huge potential, but nobody really can use an incorrect simulation result. And since a simulation potentially can run for weeks, then just trying a trial and error on the master algorithm might not be a very optimal strategy here. And also errors in the co-simulation algorithm can be very, very hard to debug, especially like for like domain experts. And the algorithm should be tailored to each specific co-simulation scenario. So we could ask ourselves, how do we catch or potentially create such an algorithm? So obviously we need a formal definition of a co-simulation scenario and a co-simulation algorithm, like how does the scenario look like, which like simulation units and their characteristics, how are they coupled together. And in the co-simulation, we want, okay, how are values exchanged, and when and how are new states calculated. So in a scenario, we describe it like this, saying we have different simulation units here. We have like the different ports here. We have some input contracts, and it's basically the input approximation function on the different simulation units. And we have like the couplings, and the couplings, that's basically a contract between the inputs and outputs, and that's at all times. So this basically just say, okay, the value on the output port here and the value on the input port here should be the same at all times. So, and also we also want to say, okay, and simulation unit may reject to take a step of a certain size. We also denote it in the scenario. So once we also have like the simulation units, and that's represent, like, as you already know, a dynamical system having a state that evolves over time. And you interact with the environment through these couplings, and then you can basically calculate its future state within some time interval. And it adheres to a well-defined interface, like we often use FMU or FMI. And the way you calculate a future state, you use like assumptions because, as I remember, the couplings, that's the contract on all times. So whenever you are stepping, like calculating a future state, then you might need to assume how the values on your input port develops in that period of time. And there's like two schemes. So we have a delayed contract, that's where you use extrapolation, and we have the reactive input ports where you use interpolation. So when we're down to the master algorithm, and obviously we want termination and time progression in it, but we also want like the way we exchange values, which we refer to as the communication points. They should minimize the error being introduced once we calculate new states. And all the simulation units, they should move in like lockstep. And if one of the FMUs reject a step, then we should correct it by backtracking the simulation and trying again. And obviously, if we have any algebraic loops, then they should be stabilized by obtaining a fixed point. Yeah, I tried to showing it like here. So synthesizing a master algorithm, it's actually quite simple. It's simply just a matter of like saying, okay, which actions should be in the master algorithm and in which order, basically. So on the which action should be in it, it's basically all the couplings restrictions, they should be satisfied, meaning for all the output ports, we should do one single get operations, and for all input ports, we should do one set operation. And then we should calculate new states for all the simulation units by performing one step operation. But what about the order? So previous research has been around, okay, especially Claudio has done a lot in this area on that like an operation or an action is not always meaningful to perform on an FMU. So an obvious example could be like, you cannot set this value here before you have obtained it here. That's sort of like a simple contract that you can denote on the set operation here. So when you calculate or when you put together all these constraints, you can basically come up with a graph-based approach where all the actions that are the vertices of the graph, and then all the edges that are the constraints you have on the actions. So here we can see, okay, that set depends on gets, and get depends on do step, and all that. And from that, it's simply just a matter of taking the topological order of the graph and using that as the like a co-simulation algorithm. Yeah. So, but there are some challenges in synthesizing such algorithms, because not all scenarios are as simple as the one you have seen before. Sometimes we have like an algebraic loop, as shown here. I'll not talk about that. Or sometimes we have the scenario where you have a simulation unit that may reject to take a step, where you should like sort of backtrack the simulation. And I'll just describe, okay, how do you deal with those scenarios? So if you have a scenario where one of the simulation units can reject a step, and it obviously rejects a step because some important information gets lost, then you need to backtrack. So here's an example of that. And here, if you just use the normal like graph-based approach, then you can't really find out and saying, okay, there's a problem here. I need to use the step finding procedure, where it's basically an iterative search. where you search for a step that all the simulation units are able to take. So basically, you could look at like the step negotiation procedure and saying, okay, if one of the simulation units reject a step of a certain size h, then all the simulation units that have taken a step of that size should obviously be backtracked. Otherwise, you'll end up having like some simulation at time 10 and other at time 15, and it'll be a mess. And of course, we want to limit the number of simulation units which we backtrack in the simulation. And when the goal is basically to find a step acceptable by all the simulation units. So with step negotiation, we want to make it visible in the draft-based approach by making it into a non-trivial, strongly connected component containing all the actions. So how do we do that? So first of all, the question is here, okay, how do we determine which action should be a part of a step negotiation procedure? And that's all the actions that we need to perform in the co-simulation algorithm before we take a step that may fail. And it can essentially be like all the operations that are part of a simulation unit that is coupled to a reactive input on a simulation unit that may reject to take a step. So in this case here, since this one can reject a step, we need, and simulation unit C is reactively coupled to D, we need to step this one before we can step D. So if D fails, then C should also be backtracked. So we just iteratively calculate the set of the simulation units that we need to backtrack here by just starting with the simulation unit D, which we know may reject a step, and then we iteratively expand the set until we reach the fixed point here. Yeah, and then we introduce some extra edges in the draft, as you see here. And as read, like we want to limit the number of simulation units that should be backtracked. And the way to do that is just we want to make them as the first thing in our code simulation scenario. So therefore, once we have this set, we just add an extra edge here to making sure that this thing is performed first in the code simulation. And yeah, so once you have this strongly connected component here, and it's simply just a matter of using Target's algorithm to finding this, and then you can just identify it as a non-trivial strongly connected component containing like step nodes and some edges between them, and then you just remove these edges and you can obtain the step negotiation procedure. That's the idea. And the tool, or we have implemented the approach as a part of a tool chain of the scenario verifier, which Casper he talked about earlier. So the idea is here that as a user you would like supply the co-simulation scenario, and it could be a co-simulation scenario with algebraic loops, or where one of the simulation units may reject to perform a certain step. And then you would use the algorithm synthesizer for generating a master algorithm. Then potentially you could use like a UPAL verifier, which we have also made to verify the algorithm. And currently we are working on integrating both the verifier and the synthesizer with the Maestro. Yes, and then a little bit about the future. Yes, we're looking more into like formalizing some of this stuff. Like currently we are experimenting with angelic non-determinism, sort of like as a formalism method for specifying the step negotiation procedure. Yeah, that was it.
Thanks, Simon. Thank you. And again, as before, you can ask questions to Simon in the chat. Now, Valerie, could you share your screen? This is one of the InterCPS partners who have been combining FMI with other things. So.
Sure.
Perfect.
Can you see my screen?
We see your screen.
Yeah. Okay, so I am Valerio, and I work in the system modeling and simulation group at Collins Aerospace. And in this presentation, I will give you an overview of how and why we integrated FMI, TRM, and VISTAS for virtual system integration. So let's start with the CPS problem. As you know, engineering a cyber physical system is a challenging task, I would say, in terms of both system level requirements validation and system level integration verification. And this is because a cyber physical system is a heterogeneous system, which is composed of subsystems coming from different domains. We have functional components, network and computational components, as well as physical components. And they should be orchestrated and integrated together, I would say, as soon as possible during the CPS engineering process to mitigate all the risks that come from a late integration. For example, one of the things that you would like to understand since early design stages is how the time delays and the failure modes introduced by the network and computational platforms impact your application. Or another example, you would like to know if there is any bottleneck in your system. Well, you can answer these questions only if you include in your validation and verification processes also the salient aspects of the CPS distributed communication and computational platform, and not only the functional system behavior. However, such early integration is usually complicated because subsystems come from different domains. Their development may follow specific design processes, and to integrate them together, there is usually the need to wait for the real hardware prototypes. In this setting, virtual engineering techniques became increasingly popular to support the CPS engineering process. When you're dealing with a virtual engineering approach, you have models of the CPS subsystems, and they are used to evaluate the subsystem and system behavior without the need of the physical prototypes. This allows performing a virtual integration of CPS subsystem earlier in the design process in order to define a virtual system prototype of the full cyber physical system. This capability brings several benefits by facilitating the evaluation of different design alternatives and the validation of system level requirements. It also increases the coverage of the testing from early design stages, and all of this is done leveraging a virtual system prototype. Now, virtual integration can be performed at different abstraction levels corresponding to different stages of the V cycle, which is shown in the slide. For example, modeling the loop is usually performed on the left side of the V cycle, and it is usually done for design validation with respect to the system requirements. On the other hand, software in the loop and virtual processor in the loop are usually performed later on the development process. They already include some real artifacts, like, for example, real software codes, real target binary code, and they are usually used for system level verification. And one of the things which is really worth mentioning is that virtual integration approach supports not only company internal engineering processes, but it is also useful for the cooperation between different suppliers, for customer-suppliers integration, where each of the two partners develops a specific component, and using virtual prototypes simplifies a lot the overall system development. Unfortunately, I have to say that virtual engineering doesn't come for free, but brings some other challenges that we need to cope with. Even virtual integration is not always easy, because in general, as you know very well, there are several tools, several modeling languages, several modeling formalisms that are used by different companies, or even in the same companies, it happens that you have different groups using different tools and languages. And this makes virtual integration sometimes problematic because you have models, people that cannot talk to each other. On the other hand, it is also true that you have different domains in a cyber-physical system. You have the functional domain, you have the cyber domain, the physical domain, and different domains usually require specialized modeling environments. And this is further complicated by intellectual property protection, which is also another important issue to address when you are dealing with external supplied subsystem components. At the root of all these issues, basically, there is, in our opinion, the lack of a standardized model integration platform, which limits a lot model reuse across different analysis and verification strategies, which limits a lot collaboration, and in general, increasing the modeling effort. And sometimes decreases also the benefits of adopting a virtual engineering approach. Now, actually, in recent years, several integration and interoperability standards have been published, but they all focus on specific domains, and they miss the vision of a multi-domain modeling environment. Perhaps I would say that FMI has the ambition to go in this direction, but in our opinion, it is still not mature enough to model many mixed, discrete, and continuous behaviors. And we will see with the next version of the standard how they will address these issues. So our approach, what we have done to overcome this limitation. So the first solution that we could think of is to propose a novel and single modeling environment that covers all the different modeling technologies. But this approach, in our opinion, would not work due to the nature and intrinsic heterogeneity of subsystems belonging to different domains. For this reason, what we chose to do is to adopt a different approach. Instead of a single tool for modeling everything, the idea is to have a tool that enables the virtual integration of models coming from different tool chains. So engineers can use the same tools they are used to and then integrate their models in this integration framework, which we call MBIF, for Model-Based Integration Framework, to finally obtain a model of the full cyber-physical system. To realize this, to implement this view, we leverage different standards, each one designed for the integration of models of a specific domain. Which standards do we support? First of all, System C TLM 2.0, which targets the model exchange of hardware components, a key enabler for hardware-software co-modeling. Then we have FMI 2.0, which targets the integration of physical processes, physical components, but also functional components when possible, when the FMI interface is expressive enough for the specific use case. And finally, we have the ED 247, which is a EuroK standard, which targets the integration at system level, where virtual and real components can be integrated together in a hybrid distributed simulation. And this is particularly useful for the customer-supplier integration problem I mentioned earlier in this presentation, because you can protect the intellectual properties, because being distributed and remoted, each partner can run the models at their sites. Now, this slide summarizes the typical usage flow of our framework. Models, as I said, can be initially developed in an external tool. For example, a controller model and an engine model can be developed in MATLAB, and then they can be exported as FMUs and integrated in our framework. Here, they can be coupled with models of the distributed network infrastructure, achieving a simulation of the full cyber-physical system. And we can study, for example, with this integrated system, how the network delay affects the controller functionality, just to give an example. Now, here I would like to mention also that models cannot only be integrated in this framework, but they can also be directly developed, because we support the standardized System C language, and we have a virtual model library of hardware and communication components that are ready to be used and to integrate it in novel systems. To support the integration of models coming from different domains and that has usually different modeling formalisms, we support several models of computation like discrete event, discrete time, and continuous times. And of course, we have implemented all the coordination logics which is needed to synchronize components and manage the data flow between them. And finally, we also support the FMI export. So once we have a system of a cyber physical system model in our tool, we can also export it as an FMU to be further integrated in other tools for other analysis. Now, before closing this presentation, I would like to spend a few words on our standardization activities, because we also try to contribute to improve the future versions of the standards that we use. For example, FMI, we know that it is good for co-simulation of physical systems where you have differential equation and time is continuous, but it is a bit of a challenge to co-simulate many mixed, discrete, and continuous behaviors. And this is a limitation for the current version of the standard, at least. So for this reason, in collaboration with some university like Berkeley and Pisa, we proposed a few years ago some modifications and extensions to the standard to be able to cover also the co-simulation of hybrid systems, where we have, as I said, this combination of mixed and discrete dynamics. Now, if you are interested, you can find the link to the paper on the top right corner of this slide. The paper has been published to the ACM memo code and discussed also at the Modelica conference. Another example is represented by our work presented this year at the System C Evolution Day, a workshop which is promoted by Accelera to advance the System C ecosystem. This year, we proposed an approach to extend the System C TLM 2.0 standards for the model exchange of network protocol. To the best of our knowledge, there is no existing standard which allows the model exchange of off-chip network protocol models similarly to what the TLM 2.0 does for IP components based on memory map buses. So for this reason, we proposed in this work an extension to the TLM standard to enable also the model exchange of network protocol models. We believe that we chose the TLM 2.0 standard because we believe that it could be really adapted to support the model exchange of network communication protocols, as it already implements the concept of transaction modeling, which is typical of network communication. And I think that this could be, apart from the CPS community, very important also for networking community people, because they usually face the problem of porting models from one network simulator to another. Last slide, just to summarize our effort for the standardization. We are currently contributing to the development of the new version of the ED247 standard, which is part of which is a Eurokia standard. As I said, we try to contribute to the Accelera and to Modelica for the FMI and TLM 2.0. And we are now participating, setting up a European initiative on hybrid simulation standardization with other industrial partners. This is something which is very new, that we are developing now, and the goal of this initiative is to not to create a new standard, but to let's say standardize how we can make the current standards that we have communicate together, basically to address all the issues which I mentioned in this presentation. And that's it.
Thanks very much for the interesting talk. It gives lots of questions to be raised by the audience in the chat. And Christian, Daniela, can you share your screen for the next presentation?
Yes.
It's good to see this combination of different standards. So go ahead, Christian.
Okay, so I'll first post a link to the GitHub repository so you can go have a look at the thing I'm going to talk about. It might help a bit. Share. I'll be giving the presentation, and because we only have 10 minutes, so it probably doesn't make a lot of sense to try to cram in 2 people. Can I please present this? I need to go into Sky for Business View. Do you see my screen right now? Because apparently
it's your screen, yes.
Okay, great. I don't know if this will do the thing. Why is nothing working? Please. There we go.
Now it's working.
Okay, so I'll be giving a short presentation on one of the tools you can use for implementing FMUs in a way that you don't have to deal with all the nasty details of it, because it is a standard that is optimized for sort of compatibility at a API level, but not for humans. So this is what I'll hopefully show you. And by now you should probably also understand why co-simulation can be useful, because we're building very complex products. We have the need to test that these things work. We might also be in the interest of visualizing these things or trying them out in some virtual reality or AR setting, where we also might need to capture user input to the system so we can actually experience the product as it's envisioned to. Hopefully by now you have an idea of what at least the goal of the functional mockup interface standard is. So it's really just to make it possible to put together models of using different formalisms, so we can hopefully reuse a lot of models and build products more quickly. And it's touted that they support more than 100 tools. And this is true to some extent, because sometimes the implementation of the standard is not 100% correct. So it's a much of a commitment to implement this from scratch. So if you want FMU, you can choose one of these 100 tools that might be free. Some of them are commercial. But the question is, what if you want to do something that is outside these domains? So if you, for example, want to do machine learning, you want to use deep learning models inside your co-simulation, you want to capture user input, or you might be interested in doing some kind of plotting or just a small sort of adapter piece of code that goes in between 2 models, then you're kind of in a bad situation. So the specification is long. You have all these C functions you need to implement, and you have to write a lot of XML schemas by hand. And this is not ideal. So what if we could take all of this stuff and put it into one box and implement it once and for all, and just use that for different languages? And that is what UniFMU can be used for. So it's a command line tool that implements this interface, and it essentially defers the implementation to the source language of your choice. Right now, this is implemented for Python and C#. The command line tool is ready to be used. I also have a GUI, but I'm not so sure that this is the right way to go. But the future will tell us this. And as you can see, this is an implementation in C# and one in Python of the same very primitive FMU. It simply has inputs of the type real, integer, boolean, and strings. And what it does is it adds together these numbers on the output whenever you call the do step. So it doesn't really change with time. It just every time you call do step, it updates the outputs. So this is what you can see in the update outputs function. And for the booleans, it adds these 2 values together. Yes, demonstration. So here I have a terminal. The tool can be installed using pip. So you just go pip install UniFMU. If I published it to the package index, but this is how it's supposed to be used. Otherwise, the instructions is on the repo. But you can use it like this. So UniFMU. You can go get some help if you want to figure out what to do. And let me make this slightly larger. Here we go. So if I want to generate something, I could try something like this, and it's going to complain that I didn't give it the right parameter. And here you can get all the choices of different source languages you can generate for. And I believe I can go something like this. If I don't have anything that's already called this. Okay. As you can see, I created a new FMU here. And let me just open this in a separate browser, separate file explorer, so I can show you what's going on. So now we have this thing. C is kind of a dummy implementation, so it's just a default example. But what is of real interest is just the implementation you have in here. So we can look this up. It looks exactly as you expect it to. Now, if we want to try this out, It's we can do this, for example, by using something like FMPy. So we can go Python m FMPy GUI, and we can then, I think we can drag and drop one of these if we're lucky. So we go in here, and now it's adding together these values. So you go something like this, and you can see that it actually changes to be the sum of these two. Now, if we want to change something, so suppose that we want something a bit more complex, we can just go in here. Let's say that we want to multiply. So when we update the output, we want to multiply this by maybe the time. So we can just add another variable like this. Here, let's set the time to 0 initially. And the do step, we can just set the time to be the current time. Something like this. And I believe without reloading it, we should be able to actually run this. And now you can see it's 1 plus 0, which is 1, and then multiplied by the time. And if we simulate for longer, hopefully it will still work. Yeah, so it goes to 10. So that's the gist of it. Where are we on time? Plenty of time. Okay. That was the demo. So how does it work? So essentially the idea is that normally you would have to implement your actual implementation of the FMU inside of a dynamic linked library. So on Windows, these are called DLLs, and on Linux, they're called shared objects, and on macOS, they're called dilib or something like this. So that's one of the pains that you have to cross-compile it also if you want it to work on all platforms. Rather than doing this, we can write a single implementation of this and simply have it call into this script, for example. And this is what I've tried to show here. So when the simulation tool calls FMI instantiate, it loads this library that you provided free of charge. And it then reads this configuration file, and it will launch a command using like process open popen more specifically. And this is also why it's very flexible. So you can have this command can do anything. It could be, opening an SSH connection into a remote computer and launching the FMU at that location, as long as it can connect back to the wrapper itself. Yeah, so I think let's just stop it here. And if you have any questions, you can ask.
Well, questions are made in the chat thing. So that's what we've done today. Because we're recording, because it would take too long to get the answers included in there. So thanks for the presentation. I suggest that Casper, if you share your slides and talk to us about the Orbit Lab in general. Thanks. We see your slides.
I'm just feeling I might be muted correctly, right?
Yeah.
All right. So you're seeing slides? Are you seeing the?
We see the slides now.
All right. Perfect.
Mode.
All right. Well, my brain is a bit full from all the presentations. I'll try and get through this. But I agreed to give a little overview of the concept of Orbit Lab and what we do. And Orbit stands for Open Research and Business-Driven Innovation Through Technology. And I'm going to try and unpack what we mean by that and how it actually is kind of relatable to a lot of the talks we saw before. Namely, how can we get all of these technologies out in the hands of businesses and make it useful in the real world as well. So first, I'd like to introduce the team. Myself, I'm a professor and deputy head of department here in the new electrical and computer engineering department. And I'm also we call it lab commander, but I guess it's like head of lab. And then we have Lide, who's our community manager, Søren, who's our technical lab manager, and then Brian, Rune, and Henrik are working on a number of research and innovation projects that we are running and also helping around with a lot of stuff. And then lastly, we have Casper and Matthias, who are our assistants. To try and explain what Orbit Lab is, maybe it's good to go to the mission. So what we do is we try to facilitate, inspire, and nurture the development of tech talent and entrepreneurial minds through a diverse community of highly driven students, startups, researchers, and industry experts. So it's kind of a melding pot of these different profiles and levels, I guess. And we do that by providing a platform for tech-centered co-creation, empowering students, researchers, startups, companies, and public sector to work creatively with digital technologies to build innovative solutions for a better tomorrow. So essentially, we want to make sure that everybody gets better at what they want to get better at, and that is the technology side of things. So everybody learns about these new technologies and what their potential are. And then we also want to create an environment where we work innovatively to try and create new solutions based on this. So we don't just work with technologies just for the sake of technology, but we actually want to solve real problems. And I think that's also highly related to a lot of the talks we saw today. So the research or technology focus in Orbit Lab is a bit broader because it kind of covers the whole department. So we work within software engineering, human-computer interaction, mobile and wearable computing, pervasive and ubiquitous systems, cyber-physical systems like here, Internet of Things, cloud computing, infrastructure, DevOps, new interaction paradigms such as virtual and augmented reality, and machine learning and AI. So we have a kind of a broad focus, but hopefully, as you'll see, it actually kind of comes together in this coherent community. So we say Orbit Lab is a tech and innovation hub. So it's actually a community of all of these different types of profiles that meet and interact around a lot of activities and projects. And a lot of these are anchored in a physical space. So we have a space at Katrinebjerg in the COT building, where we have a number of specialized labs and workspaces, open workspaces. So we have students and researchers who can come and work on their things whenever they want. And then we have a lot of also equipment and whatever you need for your projects. It also houses the Emerging Technologies Research Group. The heart and core of Orbit Lab is the community. So we launched in December 2017. So we're a bit more than 3 years old officially. We also had a bit of a beta period. And actually, as you can see, we've grown a lot over those years. I'm not going to play this video, but you're very welcome to try and see if you can grab that. Maybe somebody can, maybe Lida, you can dump the link for the video in the chat and people can have a look after if they're interested. That gives a much more vibrant kind of view of the activity. So we started pretty much from zero, and now we have, this will be, I guess, be our 70th kind of shared event, tech or entrepreneurship oriented event. We have grown the community. It's now more than 2,600 people, and we've had 2,800 people participating in a broad range of events and activities that I'll get back to. And also an important fact about what we try to do with Orbit Lab in this kind of getting out from behind the walls, as this kind of series has been called, is to open up. So we've had a lot of visitors from everything from schools to high schools, for like students who are considering to go into engineering, to companies or municipalities who are interested in exploring the potentials of these new digital technologies. Of course, we can't do all of this on our own, so we're very happy to have had some great partners along the way. We have these 12, we call them our founding partners, or founding fathers, if you will, who kind of believed in us before Orbit Lab was actually a thing. So we went around and pitched the concept, like, can we build this dynamic knowledge community embedded in the middle of the research and engineering that goes on at Aarhus University, and for all of us to share and come and have a great community to interact about all of these things. And this is a mix of big international companies, but also very strong locally anchored companies like Grundfos and Systematic and Trifork. So we've had a lot of benefit out of this collaboration so far. We also work with a lot of other companies, some big, some small, some upcoming. Some were small in the beginning. Now, recently, I think last week, Humio announced that they just got acquired for $400 million US dollars. So that was a software startup that was founded in Aarhus and has just grown because they realized how they could apply their deep technical knowledge to a problem that was pervasive in a lot of businesses, and then they made a great company out of that. So that kind of innovative mindset to have these people be part of our more academic-oriented community really helps us to think about creating value as well. And that's something we want to expose to both the students, but also to researchers, of course. Excuse me. We also work a lot with startups, like in the smaller scale, and SMBs. So we think it's super important, kind of aligned with the HUBCAP mission, is to get all of this knowledge out into the SMB segment and become useful. And then, of course, we are very active in the ecosystem around startups, entrepreneurship and innovation, both within Aarhus University, but also in the region and nationally. As part of what we do, we also have a small incubation space where students can apply and they can sit and work on their tech startups. And we've had some great companies actually come out of this that kind of graduated. They grew, they went through the whole process, and now they're fully functional companies that have left the nest, so to speak. And one of the examples of this is Cinzia, who recently left Orbit Lab. They were sitting in Orbit Lab for a couple of years, and they built a very scalable IoT platform for biological processes. So they're biochemical engineers. They have a lot of domain knowledge. They came to Orbit Lab. They learned a lot about digital technologies and the potentials of cloud computing and putting it together with embedded systems. And they built their own platform, and now they are running both research projects and industry projects. And I think it really highlights the potential of a lot of our students also to go, while they're students, to maybe start their companies or at least get experience in this entrepreneurial process, because it's a great learning process, and it really forces you to think about creating value with your technical skills. So part of making this community grow has been through a lot of events, and this is a lot of work, but it's also really great. And all of these events serve kind of different subsets of the community. So these are just some examples. So I'm just going to give you some glimpses into some of the kind of things that happens in the lab. Obviously, people can come and work on their projects, or they can come and just interact around. If we have a particular event that they want to be part of, we have a lot of equipment available that they can borrow if they need it. We have a lot of tech talks. So we have experts coming in from industry talking about not only the research side, but also what is the industry best practice for software development in large computing systems in the bank sector, for instance. We have a lot of workshops where people learn new technologies. We host hackathons, competitive programming events. So this Thursday, we will have the Google Hashcode event, which is a global competitive programming challenge where you can sign up with a team, and then you can come and work in Orbit Lab. Obviously, none of this is happening physically right now because of COVID, but we hope we can get back to this because this, we really miss having these events. So it's just a very diverse community of people from many different domains, ranging from healthcare to production to pretty much any sector. We have a lot of public sector municipalities coming in wanting to work with new technologies for elderly care, for instance. And another thing we really strive to do is to integrate this innovative kind of and new technologies into the education. So we do a lot of co-curricular and extracurricular activities that are directly linked to the courses, so that the students who have to go through a particular, if you're studying to become a software engineer, you might want to learn machine learning way before you actually get the machine learning course later in your education. So you can already get your hands dirty with some of these frameworks by participating in these events early on in your study. And that's a really good way to getting students involved in these both emerging digital technologies, but also research and innovation and entrepreneurship at an early stage in their study. So it's a lot of hard work, and of course also you got to remember to have fun. And I see some familiar faces here, previous presenters included. And you can see here an example is a highly spec'd digital beer pong table that some students made as a project. It probably has more sensors than the ship we heard about in the previous talk. So it can be fun as well. So it's about creating a good working atmosphere where people are willing to share. And then of course we also go outside the walls. So we also feel it's our mission as a university to go out and promote the knowledge and the technologies we work with, and we participate in hackathons. We go to, of course, conferences, but also events such as Girls Day in Science, things to promote getting more female engineering students that we think is very important. We can try to highlight the application of some of the knowledge you get in engineering to see that engineering is not just, sorry for saying it, boring math, which some believe, but it's actually a very creative field where you actually get to build things that go out in the real world and make a change. Right. And one of our marquee events that we kind of has evolved over time is the Orbeez. So you know the Oscars. So this is the Orbeez where we hand out prizes for the best projects that was done in a given semester. And this can be the best, most technically challenging project, or it can be the most innovative project. It can be for the best pitch. So students pitch their projects as a kind of a startup to get the more entrepreneurial mindset going. And it can also be the ones who've contributed most to the community by sharing their knowledge and helping others. So that's a large part of what we also try to create. And I think also a very important part is that we try to get people together from different fields and different levels. So we have everything from first-year students to master students and PhD students sometimes that actually can sit and work because they're all passionate about the same technologies. So if the students are really good, they get nominated and then they can win one of these prestigious Orbeez statuettes. And one of the best parts is that we always get a very high-profile expert panel to come and judge this. So it's always people from industry or researchers who come in and give the students, they challenge the students, they give them really good feedback, and you can always feel this very, very high level of energy where students feel like, wow, I didn't even think this could be a real thing, but now I just realized, you know, I talked with this person and now I have all these ideas. So bridging bridging out to the external world, both the public sector and to industry is a great way for students to grow and to kind of find a sense of purpose in what they're doing. I think I'll stop here. I think I'm on time pretty much. So if you want to follow Orbit Lab, you can stay connected in one of our channels. If you want to, you'll get notified when we have events such as this that we're kind of co-hosting together with the department and Peter. And I think, yeah, I'll cut it short here. It's been a long day.
Thanks very much, Casper. So I would like to close the meeting first of all by thanking all of you for attending now for 2 hours. As Casper is saying, it's a long time, and I'm not known to have many breaks. I hope people will take their breaks beforehand. If you have an interest in these future events, then you can see the dates of them here. And at the place where you registered for the event, you also have a possibility of informing us if you would like to give a presentation at a future event. I hope that you can also see from Casper's presentation why I decided to take the webinars we had, let's say in a more dusty fashion in the old days with the Inter-CPS Association and some of the other research projects, and taken it to this more professional level, which I think will be helpful. And this is all due to Lide, the one at the back. So in case you want to present, you can also send her an email rather than registering on the webpage for that. I'd also like to thank all the speakers for presenting their work. If any in the audience have questions to them, you are going to get hold of their slides in case they are sent to Lide. And then we will pass them on to you. Lide is probably going to send a questionnaire for what you thought about the event. Anyway, in case you have missed some of the talks because you've had other meetings, you can find the recordings on the page where you signed in a few days. And you're also going to receive an email with a link to that. So that's all for now. Thanks again for joining, and see you next time. I can see that there were a number of former colleagues and former collaborators. In case you want to chat, I'll stick around, but we'll probably stop the recording before then. So with those words, thanks so much for being here, and thanks so much for your presentations.